Nice. Hey guys, thanks for coming, everybody. Good to see all y'all. All righty, so we're still talking about memory allocation, and we fell short a slide or two on Tuesday, so I just wanted to show you that, and it was all about not that. It was all about this. I showed day one this also. We just took a couple of minutes on it. It was just that, so we were talking about this, right? This is kind of where we were in on Tuesday and looking at like, what does this process look like in memory? But we had also said that there are pieces, remember, where's our file format? Do we have it in here somewhere? Yeah, this one. So that ELF format, can anyone see anything? Am I not sharing? Oh, wait. That's some law, isn't it, Anderson? It's like, that law where you get the answer to the question moments after posting the question. Anyway, we're talking about the shape of the file on disk for an executable program, usually in ELF format on a Unix box, or Mach if it's on on Mac OS. I can't recall which one of what Windows looked like, but it had sections, right? Text section was our code, read-only data was strings and so on, immutable stuff, data for actual variable definitions and so on. Well, you can see it in the file if you want to. There's a couple of tools to use to look at that, and one of them is objdump. This thing, objdump, it's part of the shell usually. On a Mac, you might need to install it with Xcode Select, but on Unix, it's part of the shell. Linux is part of the shell. It just looks like this. Who am I? On root over here, so I must be, cool, I'm in the container. Oh, nice. By one. Yeah, so that's the Linux container. And over here, I've got test.c. So it's just a little program. Here's main, it sets up an integer called foo, and then puts a string literal out onto the console, hello world. If we run it, looks like this. Hello world, woohoo. Well, we can use objdump if we want to take a look inside that executable file and see where all the pieces are. We can just use a command called mute, record. I think we're still recording. Yes, we are. Got the chat open. I think Zoom is having some issues because we had the same problem over in GSU. Yeah, sweet. Looks pretty iffy, huh? All right, I think everyone's on. You guys, can you see everything? Great. All right, so we just ran file on that executable. You can't see the screen, hang on. There we can. There we go. So I just ran file on that executable called test, and it just tells me all this information, right? So it's an executable, that's the platform. It's basically an ARM platform. It's in ELF format. You would see Mach OS or Mach object on a Mac if we ran file on something on the Mac side, it actually, that's interesting, as a build ID. I didn't know it threw that in there. It tells me I did have debug info in it, and it's not stripped. And that's because when we ran this, we did it this way. Let's type it. So we did it this way. Whoa, holy crow. Oh no, I'm in VI. How did I get into VI? I can't get out. Quit. So we did it this way. We said GCC, which stands for GNU Compiler Collection, by the way, not anything CC-ish. -O. Yeah, everyone's stuck in VI. -O test. And then we'd use the -G flag. The -G flag for GCC, for your compiler, saves debug information. So it's going to save symbol tables off for you, possibly line numbers, so you can go back and refer to it when you're debugging. And then test.c. So that's how I built it. And that gives us, oops, that gives us this. That gives us that. Now we can do an object dump on this. Object dump is the command, and just shows us the sections. So I'll do an object dump. Let's do this first. Here's everything you can do. So these are the switches for object dump. I can look at just file headers. In fact, this is what file does. It just does an object dump and reads the file headers off. I can disassemble stuff, so you can actually see the assembly code that was generated by the compiler. I can look at the source if I want. Let's do it this way. Let's do object dump test, and let's do dash. I want to disassemble, and let's take a look at source. Big S. I'll run it through less so we can page it. So this is what object dump gives to you. It tells me, oh, what's my file format? It's an ELF. Init, like all of these pieces, these are all of the parts of our program. Start is mapped onto main. So that's the first instruction in main, and that is where execution is going to start. This stuff, that's the assembly language code that was generated by the compiler. Because remember, what the compiler is really doing is it's taking your C source code, it then compiles it down to assembly language. Then the assembly language is run through an assembler, and then that's compiled or assembled down to an object file. The object files are run through a linker. All of the objects, like the libraries we need, like if I'm using standard IO, I got to grab the standard IO.O library stuff. All that gets linked together into the executable file. So we start with C, it goes through assembly language, and then into executable format. Once this gets past a linker, we can save off the assembly language if we want. And that's what we're looking at here. So that's actually all of main. And somewhere in here, you're going to see there's going to be a read-only data portion that has our hello world string in it. I won't spend a lot of time on this. We'll actually play around with some assembly language later on in the course. We're about halfway through the course right now. So second half, we'll be playing around with some assembly language, just kind of to the point where you can sort of read it and kind of understand what's happening, like where stuff is going. That was sweet. Back here. Bernard says, why do interpreters like Python need to convert to C? Why can't they convert directly to assembly through a linker? I actually don't know what Python outputs. The language itself, Python itself, is written in C. That's not to say that Python doesn't go direct to an object format. I don't know what the path is for it. Be something you could look up. That's a Wikipedia thing, right? What am I looking for? Oh, let's find the read-only data. Not found. Where is it? Ta-da. There's my register stuff. That's main. Oh, here's main. That's cool. So you can see like it's interspersing. Oh, that's even better. I love that. Yeah, having trouble with Zoom. It's just Zoom. Unfortunately, that sounds like their servers either overloaded or under attack or something. It could be the BU network, I suppose. But look at this. So this actually appeared earlier, I think, but because we use the dash large S, capital S option on objdump, the large S intersperses the source code with the assembler, so you can actually see what's going on here. Here's int foo equals 5. This is saying move a long word. We're going to move 5 into some location that's pointed to by this register. Well, that register is holding the address of foo, so we could probably find it if we wanted to. Here is the put string for hello world. So I'm going to move a pointer to hello world. That's going to appear down somewhere in the read-only data portion. I'm going to move that into a register, and then that subroutine call here, that call is to the library function put string, put s. And then when we come back from that, now I'm going to clear out that register. That return, where's that return from? I guess that return might be from main itself. And then that no op that's just sort of a spacer, I think. But it's kind of cool, all right? Like we can see like what's actually being output by the compiler. Let me try a different version of this. If I just do the full load, let's see, I want to do headers, file headers, disassemble it, full contents. Let's go dash S. So that's the full contents of the file itself with all of its sections. We should be able to find the read-only data in here. So there's the read-only data section up at the top, and you can see what's in there. Hello world. That's immutable, so it's read-only. That's kicking you out and rejoining. Yeah, well, you guys are, Andrew, are you on campus or no? Oh, you're on campus, yeah. So it could be BU's network still. Anyway, so I just wanted to show you that. We'll be playing around with objdump a little bit more as we go. So you'll be doing like debugging directly in memory, looking at objdump to map stuff into the structures in the process in memory. We just keep going down the rabbit hole until people just can't take it anymore, and then that's the end of the course. All right, sweet. Let me bring up my other one here. Nice. What we really want to talk about today is heap operations, because as we saw over here, when we look at, so this is the structure on disk. So that's the file holding our executable and where things go in the file. Once we get into memory, it's going to look like this. So the stuff in the file is down here at the bottom. That's the data segment, the read-only data, and so on. Text is our actual code. And then just above that is the heap. Up at the top is the stack. We'll talk about the stack starting on Tuesday and do some stack operations. But the heap is down here. Memory map stuff we'll look at later also. That's going to end up being like libraries and so on that we're mapping in. But the heap is down here. The heap is where when you do a malloc or a calloc or a realloc, that memory is being assigned from the heap. So it's for dynamic stuff, for things that we're defining and actually allocating at runtime, on the fly, as we say. All right, let's pull this out, see how this is going to work. Sweet. Oh, I had the same diagram there. Nice. And by the way, just an aside that I forgot to tell A1, the locations of like where does the like the read-only portion start and stop? Where does the data portion start and stop? Traditionally, those were in fixed locations in memory, and people started using that to hack processes because they knew that the read-only data was always going to start at this specific location in memory in a process, and now it's randomized within a range. but it's just some random value within the range, just to make it harder for hackers to get in and know that, oh, that's the boundary where the heap starts, for example. So these, even though we have numbers here and they look like they're fixed numbers, they're not really, they're slightly random when the process starts up. So when a process does start up, a bunch of stuff happens. So the information in the file gets read, and we're going to have to map those things into this structure. So the purple and yellow segments here, that comes directly from the file, but there's always other stuff, right? I've got to create a pointer that points to the top of the stack. I've got to create a pointer that points to the start of the heap, and so on. I've got to actually start allocating some memory into the heap. That all happens as the program is being loaded in. So normally we're starting a program by calling a function in the kernel called exec. Exec is responsible for setting up this process. Really what exec does is it takes the parent process. So when you actually start a program, you're already running in some process. Like from the command line, we're running in a shell process. That's, in fact, we can see it, I think. Pop this puppy back up. We do a PS here. So that's the process that we're running in. That's the command prompt. And I've got, what's its PID, 8? I could go out to, is it improc /8? So I can go to, this is on the file system, I can see stuff. It's like, here's all the stuff about that process. What am I executing? It's bin bash. Do I have any files mapped into it? What's mem look like? Let's take a look at mem. Sweet. That's actually memory map stuff. Session ID, can I see the stack? Permission denied even though I'm root. Sweet. Timers, basically everything that the kernel needs to know about the process is stored here on the file system in the /proc directory, PROC. I am screen sharing, great. I'm paranoid now that I'm going to drop, but I can see that I'm screen sharing here, so I assume I'm still on. Mount, let's see if I can do mounts. Yeah, so these are all the file systems that are mounted that are accessible from the process. So there's just tons of information out here. If in your code, by the way, you need to know something about a running process, you can access the proc file system from your code and go and grab stuff like, hey, give me a list of all the file systems that are available to this process that are out here in the files entry on /proc. All right, so I'm in the context of a process. The process I'm in right now is PID 8, process ID number 8. It happens to be bash. When I do this, where was I? Let's see. I've lost my little. Yeah, nice. I've lost my silly little test program. But when I run that program, the first thing that exec does really is to copy all of the structures from the process I'm in. So I'm in process ID number 8. When I run test, it'll copy everything from PID 8 into my new process that's running test. It'll create a new process ID for it. So I'll have it, if I watched PS or top or something, I would see the new process ID show up. Or if I looked in here in the proc directory. So it copies everything over and then kind of clears everything out. But it copies the structures over and then, doesn't really zero everything out. It's really just adjusting things like where's the stack, where's the heap, et cetera, for a new process is what's happening. But a lot of the structures get copied over. It's just more efficient to do it that way. And in the context of that, so that's exec that is doing that. Exec is a kernel function that creates a new process for us. We'll run into exec and fork the two that do this when we start talking about threads in a couple of weeks. The structure is copied over, and then we start to fill it in. So we're filling in the structures from the file, from the executable file, the fixed pieces, the text portion, the data portion, the read-only data portion, all those get read in from the executable file and placed into the proper spot in memory. And then I adjust the pointers to make sure that I know where the stack is, where the heap is, and so on. And then the process goes into the runnable state, which means it's ready to run in the CPU. It's not running yet, but it's ready to run. In the context of doing all of that, so when I copy over that original, like the parent's process, the heap is essentially empty and uninitialized at that point, but exec itself starts doing some memory allocations in the context of doing its work. And as exec is allocating with malloc, the very first malloc is going to reach out to what's called the wilderness chunk. And that wilderness chunk is just sort of a whole bunch of memory that's been mapped into the process. It'll reach out into the wilderness chunk and start splitting it up, and that becomes the new heap for that process. That's how Linux does it. Mac OS does it, the mock kernel does it slightly differently, and Windows, I have no clue how Windows handles it. I think there's actually a create heap system call that gets called to set up the heap in the new process, but it's pretty different from what the Unix-based machines do. It's actually real. I should know it because Windows is based on Windows NT, which is based on Digital's VMS operating system. Dave Cutler wrote that one, or is the architect for it. So Cutler wrote VMS at Digital and then moved to Microsoft to work on the NT project. So a lot of VMS's structures appear in NT and now appear in Windows. And I used to write systems courses for VMS, so you would think I would remember all of that. But it was in the 80s, and I'm just, you just forget stuff at some point. I guess I could like do a deep memory dive under hypnosis or something, see if I could remember it all. All right, so that's how the process is initialized. It's copied from its parent process. Things are zeroed out, things are adjusted. The first few, or actually the very first malloc coming out of exec when I'm creating the process is going to start setting up the heap for me. When I get into the runnable state, the heap is already in place and I can start using it. The idea, by the way, is once a process is created, it's placed into the runnable state with the idea that it's going to run next. So it'll be created and then immediately run. That's a goal of most operating systems. Practically speaking, it doesn't always happen just because of threading and multiprocessing and so on. It's often that the new process has to wait a couple of quantums to actually run. The quantum is the amount of time that a process gets to spend in the CPU before it gets booted out. So it might have to wait a few before it gets in and starts running. And we have to make just one mention of something, which is virtual memory. There's going to be an entire lecture on this. So I'm not going to go into a lot of detail now. It's going to mention the words, basically. From our process's standpoint, we see 4 gigabytes of contiguous memory space. The process itself gets about 3 gig of that. So there's a gig boundary up at the top. It's this picture. Yeah, it's this picture. Up here, this space up here is a gig. And everything below is the rest of the 4 gig. So I get 3 gig essentially below this red line for my process. This gig that the kernel holds, I can't access. In fact, if I do try to access, I'll get a segment violation and my program will crash. So I get about 3 gig to play with. However, it's not real. It looks like real memory. From the process's standpoint, I can read to it, I can write, read from it, write to it, I can move pointers around in it, I can use it just like if it's real memory, but it's not. It's called virtual memory. It's a way for us to share memory among processes on a running system. Each process, every single process sees 4 gig of usable memory, but like this machine only has 8 gig in it. So I could run 2 processes and that would be it. There's 500 and something processes running on the box. Clearly they can't all have 4 gig of actual memory sitting on a chip somewhere. And so we use this virtual memory system that maps real physical memory into the process anytime it needs it. At any given moment, a process, probably only has a couple of kilobytes of actual physical memory that's being used by it. Everything else just looks like it has that memory, but it really doesn't. And again, we'll talk about that separately in an entire lecture. From our standpoint right now, from the process view looking sort of out, we can assume that we've got 3 gigabytes of clean memory that's ours that we can work with. A gig on top for the operating system. So let's talk about the heap. We kept running into the heap on Tuesday, just talking about it and using malloc and so on. So the heap is it's a bunch of blocks of various sizes, and those blocks make up chunks of memory. The chunks are the blocks themselves are the size of an integer. And that varies by system, right? In most Unices these days, a size of int is 4. It's 4 bytes. So you can assume that a block is going to be 4 bytes, essentially, at least when we're talking about them here. So those blocks are 4 bytes wide. And then I've got a bunch of blocks that we put together into chunks. And it's the chunks that malloc is interested in. When I ask for a piece of memory with malloc, malloc is going to look for a chunk of memory that's the correct size and then return it to me. Now, the blocks themselves are word aligned. So, excuse me. So that 4 byte block, I can't allocate 3 bytes. I can only allocate in units of 4 bytes on this machine that's using a size of int of 4. So I'm kind of limited. You know, the smallest thing I can allocate really is 1 block, which is 4 bytes. If I ask for 3 bytes, I'm still going to get 4 bytes back because it's going to give me even multiples of the block size, which is 4. I rewrite to be clear at the bottom of that because in A1, everyone's like, what? What do you mean? What's a block? What's a chunk? So I think it needs to be rewritten slightly. But I think that's pretty clear, right? So the blocks that I'm going to use are made of bytes. 4 bytes is the smallest thing I have. If I ask for 5 bytes, I'm going to get 8 bytes back because 4 bytes is the smallest unit that I've got. And if I've got 5, I ask for 5 of them, well, the next unit up is 2 blocks. So I'm going to get 8 bytes back instead of 5. Nice. We can think of, at least for our discussion, we can think of heap as being almost like an array of blocks.
Sorry, Professor?
And in this diagram, it's just showing that some are allocated, some are not allocated, some are free and some are not. And then as we do allocations against this, like we start out here, we started out with kind of a clean heap, and then I do a malloc of 4, I'm going to get 4 blocks back, and I'm just going to mark them somehow as being allocated. And then the next one is, I want 5, so give me 5 blocks. There's a 5 block allocation. And then give me 6, so there's my 6 block allocation. Now watch what happens when I free the purple one. So P2 has 5 blocks that was allocated. When I do a free, it looks like that. And then when I allocate 2 from that, there's my 2. See what's happening? I'm starting to get holes in the heap, right? These little holes of free blocks that are surrounded by allocated blocks. That can become a problem really quickly. Like this is just 3 or 4 allocations in a free. I mean, like think about if I'm just doing this constantly allocating and freeing, allocating and freeing, allocating and freeing, at some point, these little holes are going to be all over the place in the heap. And the problem is like here, what happens if I try to allocate 5 blocks at this point? Or even I have 5 blocks, right? So there's some down here. It's my laser. So there's 3 right here. I've got 2 over on this side. It's being sort of blocked by the chat window, but there's 2 blocks free over here. That's 5 in total. But I can't allocate 5 blocks because they're not contiguous. They're not next to each other. So it's not that I'm going to allocate a block here and a block there and a block there and a block there and a block there, and that they all add up to 5. It has to be one contiguous chunk of 5 before I can allocate it. So that's not good. This is called fragmentation. There are 2 types of fragmentation. Like to make it even worse, What we were looking at just now is external fragmentation. We'll get back to that. But even like within the block itself, like remember I just said that the smallest unit I have is a word, which is the size of an int, 4 bytes. So my block size is 4 bytes. If I ask for 5 bytes, I'm going to get 2 blocks back. I'm going to get, yeah, 2 blocks back. It's going to be 8 bytes long, like 4 and 4. 3 bytes are going to be completely unused. So that's called internal fragmentation. Basically, the block that I get back from malloc is just going to be larger than what I asked for because I've got to have word boundary allocations. Jonas says, why do we call 4 bytes a word? It's just a definition. Like we have a byte, a nibble is a half a byte, so 4 bits. And then a word is usually the next unit up. So a word in Unix is usually the size of an int. And on these platforms, at least, these ARM platforms, the size of an int is 4 bytes. So we just call that a word. And you might say, you might see long word or a double word, like a double word would be 8 bytes long. It's just really just a convenient word to use, word. All right, so if I ask for 5 blocks, or 5 bytes rather, I'm gonna get 8 bytes back, 2 blocks, because they have to be on word boundaries. And so it's just a lot of internal wasted space. That's called internal fragmentation. There's not a lot you can do with that really. Like if that word boundaries enforced, like you're always, almost always gonna get back an allocation that's bigger than what you need, slightly bigger maybe. I mean, you could like be really responsible, I guess, and always ask for allocations on word boundaries, like always multiples of 4 bytes. But practically speaking, like we don't know how big stuff is, you know? We just like, oh, give me this, allocate the size of this struct, like you're doing in PS3. You're building a node, you're gonna allocate it. How big's the node? I don't know, size of node. How big is it? Who knows? The chunk you get back is almost guaranteed to be a little bit bigger than the size of that struct though. Is that a problem? I guess it could be a problem. As I said, there's not a lot we can do about it, really. It's just the way the policies are written when we do allocations. So it's just always going to happen. We'll end up like playing with that a little bit to use some of the space, but it's not space that you can really use, I guess. So that's internal fragmentation. It's just based on the block size that's being returned, the minimum block size returned by malloc. Here's external fragmentation. We're just looking at it. So here I'm doing some allocations, 4, 5, and 6, and then I free 5 blocks, but then I try to allocate 6, and I actually have 6 here. There's 7 blocks free, but I can't allocate it because I don't have 6 contiguous blocks. Like now what do I do, right? Well, what we do is periodically we're going to reshape the heap. So we're going to reorganize the stuff that's been allocated so that the free blocks are all next to each other. So we're just going to move stuff around. And keep in mind that really behind the scenes, all of this is being done with pointers. So like it's not like I've got to physically move stuff around. Really, I'm just moving pointers around. Just like you're doing in when you're sorting your list in P3, you're just manipulating pointers, right? The list just sits there and the pointers change. So periodically, I'm going to have to coalesce the free space. Coalesce means I'm just going to group it all back together. And there's somewhere in here I call it coalescing. But like now, even this, like it seems like a really simple thing to do. Oh yeah, we do a bunch free space. I'll just munge it all together, right? But it brings up all sorts of design questions. Like great. Like when do I do that? Do I do it immediately when I free a block? Just immediately coalesce all the free blocks? Do you wait until you run out of space and then do it? Do you do it like on a timer every 100 milliseconds? You coalesce the heap? All sorts of design questions that we have to ask. And what's fun about Linux is that you have all the source code for Linux. So you can go into glibc, the memory manager, and I think it's in mem.c, which builds pieces of glib, which is where malloc lives. Like you can change the policy. Like literally just go in and write your own policy, read what mem.c is doing around malloc, and how it manages the heap, and then write your own policy to try something else. Like there's 4 or 5 different ways to do all of this. Just try them, see what happens. And most of the time people have already written that. So you can just go and say, hey, does anybody have like a round robin, heap allocator? And oh yeah, I wrote that. Here's some code for you. And you just plug it in and recompile the Linux kernel. And now you've got a different kind of memory allocator. Same thing with, with the scheduler. So the scheduler is the little process that runs, that chooses which process is going to run next in the CPU, because each process gets some small amount of time, like 100 microseconds or something. So it runs for that time, then it gets yanked out, something else gets to run. Well, the scheduler is really, really important because it runs all of the time. It runs at every quantum expiration. So it might be running, 1,000 times a second or more. It has to be really fast. Well, you can just write your own scheduler. In fact, as I recall, I think scheduler.c has some stuff commented out. So if you want to switch from one scheduler to another, you literally just change the comments around, and now you can plug in a different scheduler and see what it does. We used to do that all the time back in the day. Like we were trying to, for specific platforms, trying to figure out which scheduler was most efficient for that CPU and combination of hardware. And all you have to do is like plug in a new scheduler, run some tests on it, measure the speed, and try another one. We didn't have TV back when I was a kid, so we just played with the Linux kernel. Most of the changes, like most of these questions, have to do with either efficiency or speed, throughput. Most of the time, we're going to lean towards throughput because we want it's not real work, right? If I'm allocating memory, or if I'm managing the heap, if I'm combining free space and so on, that's not actual work being done by anything. That's not producing anything. It's just overhead. It's bookkeeping. It's stuff that the kernel has to do to keep track of what's happening, but it's not useful work. And so we want to keep that down to a minimum. So we try to make it as fast as possible. How much do I free? Remember the free call? What's free's signature? It takes one thing, right? It takes a pointer to the block that you want to free. Well, how does it know how big it is? If I just allocated 100 bytes and then I free it, how does the heap know that that was a 100-byte allocation? Well, like we need to know that because all I have is a pointer. And so one way to do it is to add a block to the front of the chunk that I'm going to pass back. So here, for example, I'm doing an alloc of 4. I want four blocks. And there's actually a 5th block assigned. And that 5th block sits at the head of this allocation. It tells me how big the thing is. When I want to free it, what I get back is a pointer. Well, that pointer, I know because of the way the heap is structured, I know that the previous block is going to hold the size of the entire allocation. So all I have to do is back up one. It says 5, which is one more than the actual allocation was. So I know that there are 5 blocks involved. Just look back, oh, it's 5, and now I can like deallocate all 5 of them and mark them free. So I'm actually going to keep a header. Each allocation, each chunk is going to have a header at the front of it that tells me how big the chunk is. And that way, when I do the free, I can just look it up, essentially. Now, the trade-off is clearly that, especially for small allocations, I'm adding a lot of overhead. So here I wanted 4 blocks. What was really allocated was 5. I mean, I don't get to see the 5th block. All I see is the 4 that I asked for. But there's a 5th block in there that's being used out of memory. That's real memory that has to be filled in. And so this is overhead. Here it's like 20%, right? What's it's 25% overhead, like an extra block for each 4. If it was 1,000 blocks, I guess it would be a little cleaner, but it's still an extra block for every single allocation. Do we care? It turns out that that's kind of the fastest way that we've come up with to figure out how big the allocation is. Just keep the information right in the heap. which is like the heap wants to know that. So let's let the heap keep track of it. That's how we do it. How about the free blocks themselves? So in this picture, I've got like, here's a bunch of free block, here's some free blocks, here's a bunch down here that were just freed. How do I keep track of the free blocks? How do I know like which one is free, which one is allocated, which one isn't, and so on? Well, I need to keep more information, right? So one way to do it is, this is essentially a linked list. It's a one-way linked list, singly linked list. So what I could do is, if a block is free, it's not being used, and so just stick a pointer in there, like literally in the first block, like that first block with a 5 in it, that's the header piece. But in the next block over, just stick a pointer in there to the next free block. So the free blocks themselves create almost a list unto themselves. And I can start at the front and then just walk down that list of free blocks until I find one that's the size that I wanted. I mean, how efficient is that, right? I think about when I'm allocating and freeing, and like, just remember like your work in like PS3, like you were doing a lot of pointer manipulation, right? When you deleted something from your list, there's a couple of pointers that have to be kept track of and readjusted. It's just a lot of overhead. It's not a horrible way to do it, but I guess it's an okay way to do it. What happens though if I like get to the end and like, oh, now what do I do? I got to go all the way back to the front, right? What's that going to be in terms of execution time? It's going to order n, right? Because worst case, I'm going to be looking at the last block every single time. That's an explicit list. So here I'm using the free blocks themselves to contain information about the list of free blocks. And it kind of doesn't matter, because when I do allocate this, let's say I allocate that block of 6 down at the bottom, there's a header going to be written. Actually, I can't do it from there, can I? I get to allocate 5 from there. It's going to be a header written, and that header might overwrite some stuff. If I'm using calloc, clearing alloc, it's going to actually zero out all the bytes anyway. But even if I'm just using malloc and I got a pointer sitting in one of the blocks that comes back to me, I mean, I'm going to do something with that block too. So I'm not just going to immediately access that pointer because I know it's there. All right, so let's talk about speeding stuff up a little bit. There's a lot of things we could do. Like I could hold several lists, maybe keep lists of blocks of a certain size so that I could index into them maybe. And it's like, oh, I got a bunch of small blocks, a bunch of medium blocks, a bunch of large blocks. What's the allocation? It looks pretty big. Just jump right to the large block list. That's not a bad way to do it, to split it up. I still have to do some housekeeping, but generally I think it'd be faster, right? Because if here I've got one large list, and if I had multiple lists covering the same amount of memory, each of those multiple lists is going to be shorter. So if it's still an order n operation, it's probably order 1 to get into the array of lists, small, medium, large. Probably an order 1 operation to get into the right list. And then it's still order n in that list, but n is smaller than if I had just one giant list. So it's going to certainly speed stuff up for me. Maybe if I know what the profile of my allocations look like, and this would be in like a closed system, maybe Mars Lander, I know exactly what each code branch does. I know exactly what its allocations look like. Actually, it's running Linux, so it's running Ubuntu, I believe. And so, or is it running Ubuntu or Mint? I can't recall. But it is, the Mars Lander is running Linux. So I could tailor the allocation profile. If I knew all the blocks are going to be exactly the same size, I'd probably design the heap to manage blocks of identical sizes, and I would treat it differently, because it's like a closed system, right? I'm not running arbitrary programs. I'm running specific programs, and I know what their profiles look like. For general purpose machines like our Macs or Windows boxes or Unix machines, like we don't know ahead of time what we're going to run. So it's really hard to do that sort of decision. So we need kind of a general purpose allocator that works reasonably well across all of requests. Maybe not so great in some places, but overall it works pretty fine. Multiple lists, like, you could keep it in a tree, like keep all your stuff in a balanced tree, for example, and sort them by size, maybe. So as I walked down the tree, maybe I get larger and larger chunks, or the larger ones are at the top. If I keep it balanced, like using a red-black technique or AVL trees or something, if I keep a balanced tree, I'm pretty much guaranteed that that's an order. What is it to find the bottom node in a tree? It's order n log base 2 of n, I think, which is pretty fast. Like even just terms of searches, it's log base 2 of n. So if I have 4 million blocks that I'm keeping track of, in 32 tests, I can find one of 4 billion blocks. So it'd be a really flat tree. Can I use a hash table with size of the blocks as index? That'd be pretty cool too. And then the hash would get me into, actually the hash would probably return an index into an array, and then the array would have the head of a list of all one size block. There's tons of ways to do it. We won't hit until Tuesday, but we'll take a really quick look at how glibc handles stuff. We'll see that it keeps multiple lists in an array, and we use an order 1 sort of index into that array, and then we're order n in the list itself. But there are tons of lists. It's 128 lists sorted by size, so it's relatively efficient. Yeah, this 210 is a really interesting course because like a lot of except you haven't seen a lot of this theory yet, have you? Have you guys seen red-black trees and AVL trees and so on yet? You haven't taken data structures yet, right? Most of you? We should probably do 210 after that. Although actually now that you had seen this, like when you get into the data structures, like, oh yeah, I've heard of AVL trees. Because they're really a pain in the ass. Maybe I keep implicit lists, like, oh, some data structures in 112, sweet. Yeah, because you guys know like stacks and so on, stacks and lists. Yeah, Jonas, we try to not get deep in every course. Like every professor's like, oh, I don't want to get too deep into this. And then you graduate and you never got deep into it. Yeah, 330, that's the data structures course, I think. And 350 too, at least with Rich West, you're gonna be digging deep into these structures for sure. Because remember, the 350 is the sort of operating systems intro, and they're looking at this process from the operating system side. We're looking at it from the process side, looking out to the operating system. So you get both views. So, we'll talk a little bit about this, like at least how glibc does it for all the Unix boxes, and Mach does the same sort of thing. So across the Unix-based machines, Mac OS, Linux, Solaris, all those Unix boxes, they all kind of look the same. Windows probably does it slightly differently. Actually, it's funny since I mentioned Dave Cutler and VMS, like little bits and pieces are starting to come back to me from systems courses I wrote on VMS back in the 80s. So it handles it slightly differently with a free page list. Yeah, I'm not going to go down that path at this point because I'll just sit here for 10 minutes staring into space. Not like usual. Let's go back to that kind of array view of memory and see like how can we manage memory that way and like embed information about the heap inside the heap itself. So here's so we had a header, right? So we said that header information told us the size of the allocation, the total size of the allocation. Like if I asked for 4, or I guess like looks like 3 here. Like here I asked for an allocation of 3, and so I got 3 back, but then there was an extra header block included, so that whole chunk is 4 blocks wide. But that first block is the header. That tells me how big the allocation, or the entire allocation was, and I can use that to move forward. So if I'm here, for example, I know that's 4. To get to the next block, I just move up 4, and now I'm at this one. That's an unallocated block of 6. That's actually pretty useful. Just knowing the size of each allocation, each chunk, that's very useful, I think. I also need to know though, like, is something allocated or not? Like, how do I know that a chunk has been allocated or is it free? Like, which is it? Tons of ways I could handle that. I could have a structure that kept pointers and I could keep like a flag on the pointer. So I have a list of all the pointers to all the allocations, like in a struct. And then part of that struct would be, is it free or not? And then just sort of keep that separately from the heap so I could look it up if I needed to. It's a little inefficient though, because I want that data, I want that information in the heap itself so that as I'm working in the heap, I can just immediately see that info in case I need it. So in terms of allocating, really it's just a flag, right? It's either allocated or it isn't. So I really just need one bit. And I can do it this way. So I can take one bit of that header. That header is just one word wide. Shouldn't the head block be, oh, could we make it -5 or 5? Yeah, actually that'd be cool too. Like use a negative value. I was trying to think about like how negative values are stored in memory. I might have an issue with that. Who asked that, Jonas? Jonas asked that. I might have an issue with that because it would just be slow because I'd have to figure out like, was it negative or not? So I'd have to say, is it greater than 0 or not? That operation might take several machine cycles. It's just, well, it's just one bit I'm really looking at. Here's how glibc does it, and most Unix boxes do it this way too, because they all use glibc. I can take that header information. So here I've got this header. It's a word, right? Because that's the minimum size I've got really. So I've got a word that has size information in it. Well, guess what? Remember we said that the minimum chunk that we can return is one word. So we're basically allocating on word boundaries. That means that, well, size of int, we're going to assume that's a 4 on most of our machines. So 4 bytes is that's the minimum chunk I've got, the minimum block. If that's the case, then the size is always going to be even. So it's going to be multiples of the word size. If the word size is 4, then the size of the entire allocation is always going to be a multiple of 4. Anything that's a multiple of 4 is going to be even, right? Well, that means that the last bit, like I kind of don't care about. Excuse me. And the reason is, can I write on this? Let me just write. So let's say here's an odd word, or an odd nibble and an even nibble. The first one's even, and the last one's odd. Of course, I wrote them right where nobody can see them. Come on, man. Write them up here. 1101. So the top one's even, the bottom one's odd. In binary, even numbers always end in 0. It makes sense, right? Because that bit is the oh, bless you. That bit is the, makes me crazy, 11001101. This bit is the 2 to the 0 position. 2 to the 0 is 1. How many 1s do I have? Well, in an even number, how many 1s do I have? Not any, right? Odd numbers always have a 1. So even odd, I can tell even odd based on that last bit. Well, I just said that the size of these things, the size is always going to be even because it's a multiple of 4. It's a multiple of the size of an int, which means that I don't care about that last bit when I'm calculating size or looking at size. If I don't care about that bit, I can use it to indicate whether something's been allocated or not, because I just need a 1 or a 0, allocated or free. So we'll do it that way. We're going to mask it. And when I mask a binary value, I'm essentially just doing an AND. Here are the rules. I hope you remember ANDs from CS111. So 0 and 0 is 0. Basically anything and 0 is 0. 1 and 1 is 1. So the only time I get a 1 coming out of an AND is if both things ANDing together are a 1. If I set some value to a 0 and I do an AND against it, it's always going to be 0. Anything and 0 is always 0. And so if I'm interested in the size, I can do this. So here's my header information. It's got this last bit over here, but I don't care about the last bit because my sizes are always going to be even. And so I just mask it out. Here, there's the mask. I put a 0 in that first position. And so what I get when I AND these two things together is the size I'm interested in. It's 1, 2, 4, 8, 16. That's a 32. So my size is 32. Conversely, if I want to know whether this block is allocated or not, I do the opposite mask here. So I mask out all of the size information, and I just am interested in that 1 bit. That's why there's a 1 here in the mask. So if there's a 1 there, 1 and 1 is 1. If there's a 0 there, 1 and 0 is 0. So that masked bit will fall through the AND, and I can test it now. Now here I'm just using 1 bit, but if I needed 2 bits of information, just move the mask over by 1, and then I can see 2 bits of information. In this case, I'm just using 1 bit, but you can have a mask of any size. If you guys, you guys probably haven't taken networks. If you end up taking networking with me, 455, which I don't teach very often, but we talk about network masks all the time in there. And in fact, as we move deeper into the system in this course, you'll see masks all over the place too. It's just an easy way to extract a specific piece of information out of a larger binary value. Yeah, let's make sure there's no extra questions. Cool, all right, masking is actually pretty cool, I think. All right, so now we've got a way we can actually embed the size and an allocate bit in that single word header at the start of each of these allocations, these blocks. Well, how do we find a free one? Well, we could just look at the header word, right? Just look at the header and you can see whether it's allocated or not. And we see what the size is, it's right in that header. And if I've got free blocks that have a pointer to the next free block, or I've got some way to get to the next free block, I just walk the list of free blocks, just seeing if it's the right size or not. The goal here is to return a block that is, a chunk rather, that is as close as we can get to the allocation that we asked for. It's going to be aligned on a word boundary, so it's always going to be a multiple of 4, but we want to get as close as we possibly can. And of course, it's computer science, right? There's like 9 different ways to do it. I don't know why we can't just pick one way to do things and then run with that. I don't know why. Everyone has to pee on something to make it their own. So here are some of the ways we can try. We can do first fit. So first fit says, we're sort of talking about this sort of array look at memory. I'm going to start at the front. I'm just going to keep walking down the list until I find the very first block that is at least as large as I'm looking for, and then return that. As you can imagine, there's some issues with this. You know, the first one we tell you is always the one that's got all the problems, right? Well, for one thing, it's order n, because worst case, I'm going to walk the entire list every single time. Is that bad? Like, order n is not horrible, I guess. It's not as good as a tree, which is order more log base 2 of n. But like, it's just okay, right? Because if the first one I find that's at least as large as what I'm looking for is really big, like, it's probably going to return the entire thing. And I'm going to have a massive amount of internal fragmentation, just wasted space in that returned chunk. Like, that's probably not what I'm really interested in. I can kind of like expand that a little bit and try something like next fit. So instead of starting at the front each time, just keep track of where you did the last allocation. Just have an extra pointer. Where was the last allocation? And start looking from there. The assumption being that, you know, my program's running. I'm probably like your list operations. You're kind of always, you know, building structs out of it, so they're all roughly the same size. Well, if I just looked at the first half of the list and they were all not the right size, why go back and start over again? I'll look at them again. They're still not all going to be the right size. So just start where I left off, keep going from there, and return a best fit from there. And that's not horrible either. At some point, you got to wrap back to the start of the list. You got an extra pointer to keep track of, and it's still a first fit kind of thing. So you're going to have a lot of internal fragmentation, just wasted space. It's an easy one to write. That's, for sure. First fit and next fit, those are easy allocators to write. We can try a best fit also. Best fit says, I'm going to keep looking until I find one that is as close as I possibly can get to the allocated or the allocation request to reduce internal fragmentation. That's a harder allocator to write because I got to look at the entire free list. If I'm doing best fit, I'm probably going to use a system that has multiple lists so that I can get into a list of free blocks that is pretty close to what I need to begin with, and then just grab one from there and, not worry so much about the internal fragmentation. It's going to be slower, of course, because now I've got to make some decisions, right? I got to test sizes. I might have one that would work for first fit. It's like, yeah, that's a little too big. Toss that one out. Let's keep going. Maybe I can split large allocated blocks into smaller pieces. And actually, in a best fit algorithm, that's not a bad way to go. So I get into, here's a bunch of blocks. This looks really, really big. Just split it. Just split it into the right size and leave the size, the stuff that I didn't need. So if I needed 6 and I'm looking at an 8, just split it at the 6, leave the 2 there, and return the 6 that was asked for, kind of like this. Like here it's asking for a 4. Like, I've got a 6. 4 is pretty close. Yeah, we'll just split that into 2 pieces, return the 4, and now I've got a piece of 2. The issue with this, as you can guess, if I'm doing a lot of splitting as I'm allocating, I'm going to end up with a lot of external fragmentation. External fragmentation just means I've got holes all over the place in the list. And at some point, I'm going to have to bring all those holes back together into one giant piece. So there's a lot of overhead on this one. It's probably the better of the ones we've seen so far. But what about freeing something? When I'm freeing a block, like now, if I've got all this external fragmentation, I'm starting to do freeze and so on, like even here. So I allocated the 4, I split that 6 into a 4 and a 2. I passed back the 4, and now the 4 is being freed. So this chunk is the 4 that was freed. The 2 that's from the split right next to it. And then I treat it to malloc 5 blocks. Well, I can't. I don't have anything in here that's got 5 contiguous blocks. I've got a 4 and I got a 2. There's a 4 over here. None of those is 5. And so I just can't do it. I get either a null back here, or I'd have to expand the heap, make the heap a little bit bigger, and then split off of that. What we really want to do is, like, as the program is running and using this heap, freeing and allocating, periodically I want to combine or coalesce those free blocks back into one chunk so that I've got larger chunks now. I can go back and split if I need to. Like here, I just don't have 5. But if I combine the 4 and the 2, that gives me a size of 6, and I can split it, into a 5 and leave the 1. So I want to do that essentially. I just want to, really all I have to do is clear the allocated flag. So I had this guy, this guy over here, like it had a size, right? So really all I have to do is just change that size, and that goes away. And in fact, the way it did it here, that's kind of cheap, huh? So look at what it did. So here's my 4 and my 2. All I really did was change the size value in the header here to be 6. And as I'm going down this list, I hit a 6. Oh, the next block is 6 away. And so this chunk of 2 just kind of disappears at that point. It probably still has a 2 in its header, but there's no way to get to it. So it looks like 6 altogether. That's not a horrible way to do it either. How about this problem? It's always a problem. Like computer science is always that, right? We fix something and then two more problems appear, and then we go fix those two, and now I've got four problems. Well, this is a singly linked list. I start at the top and I walk all the way down to the bottom, then I start back at the top again. If I wanted to coalesce upstream, so if I wanted to like start here and coalesce with this guy, I don't really have a way to get back there because I don't know. I don't have a pointer. There's no pointer down here pointing back here. And there's no size information about him, right? So I'm here. The only information I have is, oh, the next chunk is 2 blocks away. There's no way to get back. One way to fix that is to stick another header in, or in this case, a footer. So I just use an extra piece of memory right here. So now I said, oh, cool. So I'm here and the next chunk is 6 away. So I go up 6 blocks. But now when I'm in this chunk, where's the previous chunk? It's 4 blocks away. So now I'm in the previous chunk. Where's the previous chunk here? 6 blocks away, and so on. Really, all I'm doing is duplicating the header like this. So that entire chunk has a header at the top with a size and an allocation bit. And at the bottom also, there's a word that has the size and the allocation bit. And by using that, I can go backwards or forwards through this, even though it's a singly linked list. What's the downside? Now I'm using 2 extra words for every chunk. If my chunks are small, that's a lot of overhead. If the chunks are large, like I kind of don't care. But if 2-word chunks or 4-word chunks, like that's probably an issue. Do I care? Probably not. This, by the way, is how Unix does it. And so the Mac does it this way, Linux does it this way, Solaris does it this way, et cetera, et cetera. So the heap has chunks that have headers on both sides. We also might do something like this. So this is the way Unix does it. Here's another approach called the buddy system. This one actually isn't bad either. This might be how Windows does it because it feels really familiar, which means I was probably writing about this in the 80s back in VMS. The idea with the buddy system is when I'm going to split blocks into split chunks into 2 chunks. When I split them, those 2 chunks that result from the split are buddies. I'm going to keep track of both of them. And once both of them are free, I'm going to move them back together. So here's somebody in A1 when they saw this diagram said, good Lord. But it's easy. It's easy. Where's my laser? There we go. So I'll just walk through it, right? I start out with a 1 meg chunk and I get an allocation request for 100K. Well, the idea is I'm going to keep splitting the chunk I'm looking at, just keep splitting it until it is just big enough to hold the allocation. If I split it again, it's too small. So I'm asking for 100K. I take the 1 meg chunk and split it into 2. So now I get 2 512K chunks. Now I'm looking over here at a 512K chunk. Well, it's still pretty big, so I split it. I get two 256s. 100K divided by 2 is 256. So I get 2 of these, and it's still too big, right? So split it again. I get 228K chunks. So the way the buddy system works is I split first. This guy is buddy to all of these. When I split this one, now actually this guy is a buddy to these 2. I'm splitting them again. Like here's a split of a 128K piece. These 2 are buddies. These 2 are buddies. Both of those and that are buddies. Both of those and that are buddies. All of that and this is a buddy. And then we coalesce them back into 1 meg. But you can see how it works, right? So anytime I do a free, so here I'm doing releases. I'm freeing. I end up down here where I've got this allocation, and now I'm going to free this guy. When I free this guy, these 2 buddies are now both free. I'm going to bring them together, coalesce them. So I free here, coalesce these 2. Now that's a 256K chunk. Its buddy is free, so I combine those two and I end up here. And now when I finally free up this guy, now this is free, that's free, those two are buddies, combine those. That whole thing now is a buddy with this. They're both free, so I combine both of them back to a meg. So I'm constantly splitting and keeping track of the buddies to make sure that, what was this? Oh, it's like a game? Oh, fun. Which blocks aren't buddies? Which blocks are not buddies? Well, I guess indirectly they're all buddies, right? So even this guy, he's a buddy to these things. And even as I further split these down, that whole piece is still a buddy with this guy. So you got to find the block that's sus, right? And that's the one that's not the buddy. So that's a buddy system. But there's still questions, right? It's like when do we split? Should I coalesce immediately when something's freed, or can I wait? Can I defer it? Maybe wait until I get a free list that's of a certain size and then start coalescing. Like all of these questions, these are all questions, implementation questions. Like we can talk at a high level, generically how memory management works, but at some point you got to start writing code. And at that point, now you need to start answering these questions. All right, this is where we stopped in, oh shoot, I'm 2 minutes over, I'm sorry. This is where we stopped in A1, I'll stop here too. On Tuesday, there's just one or two more things I want to talk about. glibc, let's talk about how glibc does it on Tuesday. We'll start looking at stacks and just continue our journey down into the system. If you have any questions on problem set 3, please post them on Piazza. A lot of good questions so far, and we're trying to answer those as quick as possible. Otherwise, have a good weekend. I'll see you all guys Tuesday. Go enjoy the weather. It's beautiful out. 70. All right, peace out. See ya.